Let's look at the first one, which it should be the kind of question we would be happy to see on a test. Like if this is the linearization you see on the test, you're like, yeah, this is good to go. We have to, as is typical, kind of figure out two things. You need to figure out what your function is, and then what your nice a value is. So what's the function going to be? Well, you can pick lots of different functions. Like there are some questions on your homework where it's like, do the linearization of like the square root of 2x plus 1. That's not the function I'm going to pick here. I'm going to try and make the function as easy as possible. And the way we're going to do that usually is just by replacing the number with the variable x. So I'm just going to, okay, my function, I'm going to use, no, this is my terrible pen, sorry. I'm dropping the pen. My function is going to be the square root of x instead of the square root of 98. And you might want to go ahead and just write down the derivative because we know we're going to need it. So if I'm going to think of this as x to the 1/2, because that makes it easier, my derivative is going to be 1/2 times x to the negative 1/2, or as I prefer to write it, 1/2 times the square root of x. Thanks. Great, we've got the function, we've got the derivative. We need the a value. We're trying to pick a number that's easy to take the square root of, that's close to 98. What's our best candidate? 100. But if you didn't know what it was, you might start just taking square numbers, right? So you'd be like, okay, well, I know that 8 squared is 64, 9 squared is 81, 10 squared is 100. Oh, okay, of these three, this is definitely the best candidate because it's the easiest one to do that's the closest. So it might not seem so challenging for squares, but if you're doing like a cube root or a fourth root or a fifth root, that's also the same way you go about trying to figure out what's your nicest, best choice. Welcome, welcome. Thanks. All right, so we've got all the things we need. We just have to throw it all into the formula. Again, if you don't remember what the formula is, and I often don't remember this formula, it's the equation of the tangent line. So if you have to go back and be like, okay, it's y minus y1 equals the slope times x minus x1, and then rewrite it as y equal to y1 plus the slope times x minus x1, that's a perfectly okay thing to do. You don't have to memorize this formula, although it comes up frequently enough that you probably want to, but you don't have to. But if you're ever confused about like if it's a plus or a minus here, you can remind yourself, oh yeah, it's the equation of the tangent line. I know how to find the equation of the line. So then we want to find all the things. We want f of a, which is the square root of 100, which is 10. And we want f prime of a, which is 1/2 square root of 100, which is 1/2 times 10. Thanks. I definitely think it's easier to plug in 100 here than it is to plug in 100 here. Like, right, 100 to the negative 1/2 seems not as easy to conceptualize as 1 over the square root of 100. So whatever way works best for you, but think about what makes it easier. All right. Oh, I can't quite see it. Thanks. It's weird that some of them come like small, some of them come like super big. It's interesting. So now we just want to throw everything into the formula. So our linearization is going to be f of a, which is my 10, plus f prime of a, which is 1/20 times x minus what? Yeah, I feel like this is a place where it's easy to accidentally plug in 10 or like something that's not the a value, right? Because sometimes you feel like it should kind of be small, but no, it should always be what you're going to try and be close to. Right? We know the number we're actually trying to plug in is 98. The thing you're plugging in should be close to the thing that's right there. So now if we want to estimate the square root of 98, that's going to be approximately the linearization at 98. That's the whole point of doing this. Is we're just going to take 98 and throw it into that formula there. Before we get an answer, should the square root of 98 be a little bit bigger than 10 or a little bit smaller than 10? Smaller, right? So it's good to think about what should our answer look like. Oh yeah, it's going to be a little, but it should not be like super far from 10, right? It should be like 9 point something. So let's see here. I'm going to get 10 plus 1/20 times 98 minus 100. Oh, I know what I was going to say. Before you do this, he's not here right now. Anyway, you don't want to simplify this. Right? You totally could simplify this. You totally do not want to simplify this. It's not going to make, right? We talked about this last week too, where we had like, if we simplified it, we had like 32 times 0.4 or something, and that was just not something we wanted to deal with. So definitely don't simplify this, because the idea is that this amount's going to be small times something that's not terrible to multiply by if this is small. So we're going to get 10 plus what, -2/20. So that's going to be 10 minus 0.1 or 1/10, however you want to write it. I'd probably go decimal here since it's easy. My answer is 9.9. I don't actually know what the square root of 98 is because I didn't bother to check it out in my calculator, but I'm sure it's pretty close. Yeah. I don't actually know if it's an over or an underestimate. We could graph it to find out, but I don't think we, I mean, right, you could, no, I think we can leave it at that. Okay. Sorry, all these folks over here. Welcome, as usual. Yeah, you guys have questions, feel free to ask them. Questions? Observations? Our
equation would have been like cosine. And the parentheses would be, we could just x them instead of cosine of that. And like where x minus 100 is, we could just.
That's a good question. So I think we would just put the x minus 100. But let's actually go ahead and look at the next example, because we're going to totally see that thing in the next example. So very good question. I know exactly what homework problem you're talking about. This is very similar to that homework problem. Okay. So yeah, let's go ahead and see. So we want to estimate sine of pi plus 0.03, which I will tell you, although you might not believe me, this is kind of the easier version of the way you can ask this question. Someone who is less nice might ask this as something like find sine of 46 degrees, which is definitely a more challenging way of asking questions. But since I didn't see that for anyone's classes, like has anyone been asked that kind of question? Like to find sine of 46 degrees, or maybe cosine of 31 degrees. Anyone seeing questions phrased specifically that way where it's in degrees? It's a little dark. Thank you. All right, no one has seen degrees. Awesome, great, you guys are in luck. That's kind of the best possible situation, because it's much easier if it's already in radians, which this is in radians, right? If there's not a degree symbol, it's in radians. Okay, so we're going to estimate sine of pi plus 0.03. Now, I didn't write all the words, but if we see estimate something like sine or cosine or square root of something, the implication there is using a linearization. Unless they're taught, I don't think anyone's covering Newton's method. So if you cover Newton's method, we'll talk about that, but I don't think we are. So I'm not going to sweat it unless we get there. Same process. We need to identify a function and the nice value we want to plug into that function. Now this one feels a little bit, it's a little bit weirder here because you got a pi plus 0.03 instead of just like a number on its own, but that's still your number, right? Pi plus 0.03 is some number. It's like 3.44 stuff. That's what we want to replace with x. I'm going to write my function as just sine of x. It would probably also be fine to do sine of pi plus x, but you want to make your function as easy as possible because you're going to have to take the derivative of it. And so you might as well just make it x, unless there's a really, really excellent reason not to, which I don't see there being. And we might as well write the derivative, and everybody should be able to tell me what's the derivative of sine. Thank you. Right? And then they've tried to make it obvious here. What's a very, very easy value that's close to pi plus 0.03 that's easy to take sine or cosine of? pi, right? It's just the part here. Right? If you see a number plus a tiny bit, it's the number that's close, right? This is your a value right here. And that's almost always true, right? If they're giving, especially if they're right, like I didn't do it that way. In this previous problem, I was trying to, do the square root of 98. If I was trying to make it super obvious, I might have written it as, I could have written this as estimate the square root of 100 plus -2. And then I can, right, to make it be like, oh yeah, there's your a value and there's your little bit that's off by. That's what they're doing here. They're saying, oh yeah, pi is definitely the value you want to use. And the 0.03 is kind of the inconsequential part. Not completely inconsequential, but like the less important. So a is definitely pi. And more generally, when you're talking about trig functions, right, the nice values you should be thinking of are things like pi, pi over 2, pi over 3, pi over 4, right? All those nice angles on the unit circle that you're supposed to know how to find sine and cosine of. So there's definitely an expectation that we could find sine and cosine of any of these things. Okay, so we've got all the pieces. Now we just need to, actually, I suppose we don't have quite all the pieces. We should probably write out what f of a and f prime of a are. So f of a is going to be sine of pi. F prime of a is going to be cosine of pi. All right. Any brave volunteers for sine of pi? Does anyone want to tell me what sine of pi is? I know you all want to. All right, so if you don't remember what sine of pi or cosine of pi is, there's the unit circle. There's the very abbreviated version of the unit circle, which my wife always hates when I say this. I'm going to mark the 4 corners of the circle. Yes, I know a circle doesn't have corners, but it's easier than saying the 4 cardinal directions of the circle. So the circle has radius 1. This point's 1, 0, 0, 1, -1, 0, 0, -1. And if we start here, which is where we start when we're talking about the unit circle, right? The positive x-axis where the angle is 0. This is an angle of 0 radians. And then if we go this much, what's our angle now? Pi over 2 radians or 90 degrees. But yes, I agree. Pi over 2 is what you want. And then down here we are at pi and then 3 pi over 2. And then back all the way around to 2 pi. So if you specifically have one of the quadrantal angles, pi over 2 or pi or 3 pi over 2 or 0 or 2 pi, you can just draw this picture and then say, okay, I know that which one's the x and which one's the y coordinate. Good news, it's alphabetical. X comes before y, cosine comes before sine. So the cosine is the x coordinate, the sine is the y coordinate. So sine of pi is going to be 0. And cosine of pi is going to be -1. But it wouldn't surprise me to see a question like this on an exam where you actually have to be able to evaluate sine or cosine of some angle. And then after we get all this, it's time to put it all into the formula. Right? You should know what the formulas mean, but it's just the equation of a tangent line. I like to write it out every time because I just do. So there we are. Our linearization at x is f of a plus f prime of a times x minus a. And then we're actually going to put in what we've got. So it's going to be sine of pi, which is not exciting, 0 plus cosine of pi, which is -1. Times x, which we're not plugging in for yet, but we're about to, minus a, which is pi. We probably don't really need the 0 there, but it doesn't hurt. And I do think I know web work, you don't have to write like this out, you just get the answer. But like, I do think it's good to think about what you're saying. So this next part is, we're trying to use this tangent line to estimate a value. And if you want the picture, right, here's what we've got. So we're estimating sine of something at pi. Sine looks kind of like this. a sine. I'm almost about to draw cosine accidentally here. The sine starts there, then goes there, then goes there, and vaguely looks like this. And so what we're saying is, all right, I'm plugging in a number just a little bit bigger than pi. There's pi plus 0.03. And instead of trying to find the function value over there, I'm using the tangent line and plugging in and getting a value that's over there instead. But again, this should be a very, very close estimate. I know my picture is not excellent there. It's kind of hard to see. Let me zoom in a little bit, see if it helps a little. You can see, right, we're plugging in this slightly larger value and we're ending up a little bit lower over there. Okay, but if we actually do it, we're just plugging in pi over 3. So we're going to say that, sorry, not pi over 3, apologies, pi plus 0.03. And that is our approximation of sine of pi plus 0.03. I like writing this. I feel like this helps me remember what I'm doing. That, oh yeah, I'm using this linearization to approximate the thing that they've asked me to estimate. It also makes me think like, oh yeah, this is actually what I'm supposed to get my, oh, sorry, I was pointing at the thing you guys couldn't see because I zoomed in too much. Right, I'm trying to do this estimate here, and that's what I'm doing. It's about that. And then I'm just taking this previous line and substituting in pi plus 0.03 for x. Again, you could probably simplify and it wouldn't be terrible. I still don't think you should. I think you really want to plug in before you do any sort of simplification. It would be -1 times pi plus 0.03 minus pi. I don't think you need parentheses there, but. And then the pi's are going to cancel and we're going to get -0.03. And if you put that in WebWork, it's going to be not right because the question on WebWork specifically asks for a fraction. So 0.03, that's not 3/10, it's 3/100. So it's -3/100, which seems unnecessary, but it's what they asked for. So go figure. Now, do be careful. There was another problem I was helping someone with as well, where it had the same sort of restriction where like, oh, I think the answer ended up being like 7 plus 1/14. And we tried entering that, which is usually fine in WebWork, but we had to actually write it as a, it was 7 minus 1/14. And we had to write it either as an improper fraction, which was like 97/14, or as a, I think a mixed fraction was also allowed, which would have been like 6 and 13/14, which just seems like a weird thing to type in. But those are your options. So make sure you read what the question's asking you to do, because you might be right, but just not be entering it correctly. Okay, let's see. Oh yeah, there was another one. There's definitely one more I want to do. And then we can talk about the, well, there's another variety of questions, of linearization questions, where you're asked to like talk about like the percentage change in the function or the, right? But there's one other one I want to do just to give you all, to remind you all of something that we've seen recently. So let's say we want to approximate, estimate, whatever words you want to use, the inverse tangent of 1.02. Okay, so let's go ahead and also you might write this as the arc tangent of 1.02. If that inverse notation is throwing you off, which it can sometimes because it can be kind of confusing, it is also perfectly fine to write it like this. This is an alternate notation, which is accepted world round. So if you don't like this, use this. Perfectly fine. But yeah, I should, no, yeah. Let's see here. So just like before, we want to identify the things. We want the function. We want the a value. Every time I'm doing this, when I'm asked to approximate function of value, I'm just replacing the numeric value with x. So I'm just rewriting this as, oh, my function is the inverse tangent of x. And we know the derivative, or we're supposed to know the derivative. The derivative is 1 over 1 plus x squared, or 1 over x squared plus 1, whichever way you want to write it. All right, so here's a slightly harder question. Well, maybe not. I feel like I've written in a way that's hopefully obvious enough. What's the value of a that's close to 1.02 that should be easy to take the inverse tangent of? Well, let me lop off the end of that question. What's a value that's close to 1.02 that probably should be easy to plug into a function? 1, right? You've got something 0.0 whatever. It's probably just the number without the point whatever. Now, we should actually know how to plug that in. So if I'm asking, if I'm asking for f of a, which is the inverse tangent of 1, we're trying to find an angle. The angle that if you took tangent of that angle, you would get 1. I know there's lots of answers, but there's actually only one correct answer. So what is the most typical angle that you take tangent of and you get 1? You can tell me in degrees or in radians. It's a good question. So here's a triangle. And in this triangle, is tangent equal to 1? I should back up. Is tangent of this angle equal to 1? It is, because tangent's the opposite over adjacent. And this triangle, these sides are the same. These angles have to be the same. You guys want to tell me the angle now? Half of that. 45 degrees. If this angle is 90, these two angles add up to 90, which makes them each 45. And 45 degrees in radians is going to be pi over 4. So that's the angle that we're looking for. Tangent of pi over 4 is equal to 1, which means the inverse tangent of 1 is pi over 4. And definitely, definitely, you want to be using radians. Degrees, I don't think, are really an option in this class. Like they could come up occasionally, but most of the time, radians is the way you want to be doing things in calculus. All right, so we've got f of a, inverse tangent of 1, which is pi over 4. And we know that f prime of a is going to be 1 over 1 plus 1 squared, which is 1/2. We've got all the pieces. Now we just have to put them into the function or the equation. Our linearization, once again, is f of a plus f prime of a times x minus a. And now let's see. F of a is pi over 4. F prime of a is 1/2. And x minus a is x minus 1. Our final answer is not going to look very nice. That's okay. You still should do it this way, meaning you don't want to try and simplify this until after plugging in. So now we're going to approximate the inverse tangent of 1.02, which is going to be our linearization at 1.02, which is pi over 4 plus 1/2 times 1.02 minus 1. And that's lovely. It's pi over 4 plus 1/2 of 0.02, which is pi over 4 plus 0.01. I don't see a reason. I mean, okay, you could get if you had to write this as a fraction, you could write this as pi over 4 plus 1/100th. And then I guess you'd multiply pi over 4 by 25 over 25 to get 25 pi plus 1 all over 100. But I want to emphasize here, our answer is very close to pi over 4. Which is always the case for these kinds of problems, that the answer you're getting is close to what you would have gotten if you just plugged in the nice value, or I should say your answer is close to f of a in general, right? Whatever your f of a is, the thing you're plugging in isn't that far away from it. Since our functions are all, the functions we're doing this to are continuous, and there's not like a giant leap from one value to the next, you're going to get a value that's close to the thing that you already evaluated and got. Or what do you guys think? Questions? Concerns? How do you know how to do it the right way? There's a few steps, but it's always the same steps, right? I'm always taking my thing I want to estimate or approximate, replacing the number with x, that's my function, taking the derivative because I know I'm going to need it, and then the a value is just the number that's closest to that, that's easy to deal with. So we're not going to, I'm just going to point out one more thing. We're not actually going to do this one, but I'm going to give you guys the opportunity to answer a couple of questions. If I said to estimate, sure, the cube root of 127, I'll give you all a minute to write down two things. What's the function? What's the a value? You have a minute. On Zoom, if you want to type to me the a value or the function, you're certainly welcome to chat it to me to let me know you're doing it. Yeah, you can see the three there. Excellent. Yes, that's totally correct. All right. I think you have something like that. All right. The function is definitely the cube root of x. Yes, you could totally make a lot of different choices, but this is the one choice you should make. The a value might be slightly harder to find. So let's pretend like we didn't just know it right off the top of our heads. If you don't know what value is close to 127, it's easy to take the cube root of, start finding cubic numbers. You can start small. Okay, it feels kind of silly to start that small. But 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. You technically should look on either side of 127 to see which one's closer, but I think you can all see that 5 cubed is definitely going to be closer than 6 cubed. And 6 cubed is what, 216? This is definitely the one. So that's your a value. It can be a little bit harder to get the right a value if someone gives you something like estimate, I don't know what, the square root of 41. Our function is definitely the square root of x. But then I really kind of do want to write out what the closest, what my squares are to see which one's closest. So I know that 5 squared is 25, 6 squared is 36, 7 squared is 37. This is 37, holy smokes. 49, which is closer, 36 or 49? 36, but not by a lot, right? I mean, it is closer. So this is definitely the a value we would use. So you always want to pick the closest thing that's easy to plug in. All right. But then we have some other interesting questions, which some of these homework questions are phrased very strangely, I feel like. Here's an example of one, which I'm going to modify a little bit. So the value of x is measured at 5, accurate to within 4%. the function is 1 over 1 plus x. And we want to find a couple of things. We first want to estimate the absolute value of delta f, the error in f. And then we're also going to find the percentage error. Which is, they write this out in your homework, delta f over f times 100. So we're gonna do those two things. And this always feels like, I feel like this language just feels kind of weird. Like x is measured at 5. That just means x is 5. But it feels kind of weird. And I think, although we can write out some formulas, I think it's actually kind of nice to just look at a picture to see what's happening here. So let's make this picture kind of ridiculously large. Here's my function, 1 over x plus 1. I don't particularly care how much it looks like that. And we're measuring this at 5. So let's say 5's right there. And we're measuring it accurate within 4%. Sorry, I know you can't see all that. Apologies. It's always hard to keep everything on the screen. Okay, so we're measuring that at 5, accurate within 4%. Which means you're going to go 4% to the right or left of 5. 4% of 5, okay, we can calculate that. 4% of 5, that's just going to be 0.04 times 5, which is 0.2. So that means we're going to go to 5.2 and over to 4.8. And that change there, that's your delta x. And what we want to see is what your change in f is going to be. So we're going to approximate it. So instead of seeing how high on the function we go, what we're going to do is we're going to use the linearization. There's going to be some tangent line at this point. And what we're going to see is that we're going to go up to here and up to here. And this, that's your function value, that's your f of 5. And then these differences here, and hopefully you guys can see that all right. Let me get zoomed in there. This part here, that is your delta f. It's the, or I should say, it's your approximation of your delta f. So I suppose I should really be calling it df. That's your df. And df is your approximation of delta f. Let me show you, right? If you actually went up here, that would be, gosh, it's so hard to make this all look somewhat decent. That would be your delta f. But the idea is we're going to use df to approximate delta f, where df is just, it's the rise. So from here to here, how much change, how much rise is there in that line? Well, we can find the rise over the run is the slope. So if we're just trying to find the rise, it's going to equal the slope times the run. Or in less vague terms, if we're trying to find the rise, that's going to be our df, and it's going to equal the slope, which is the derivative, times the run, which is the change in x. That's how we're going to approximate the error in the function. Again, this is just your slope times your run. Okay, so now we're actually going to find the things. And this is where, so this is where I like to, this is why I've drawn this picture, because I think it feels much easier to be like, okay, well, I can find the slope of this. I know my function. So I've kind of gotten all over the place here. I know my function is 1 over 1 plus x, or maybe more easily, 1 plus x to the negative 1, because we're going to want to differentiate this. And the derivative is going to be negative 1 times 1 plus x to the negative 2 times what? Right, because it's right, negative 1 times our stuff to the negative second times the derivative of our stuff, which we're not going to write down because it's just 1. And then we're going to actually find the slope of that tangent line at the point 5. So our derivative evaluated at 5 is going to be negative 1 times 1 plus 5 to the negative second, which is going to be negative 1 over 36. So that's our slope. And then the change in f is going to be our slope times how far over we go. Right? If you went over 36, you would go down 1. We're not going over 36, but it's the same idea. We're going over 0.2. So I'm going to write this kind of in a weird way at first, and then I'm going to talk about how we did the calculation. Here's what we're actually going to get. We're going to get the df in absolute value, because you're always taking absolute values here, is going to be the absolute value of this negative 1 over 36 times this 0.2, which ends up being positive 0.2 over 30. I always feel terrible writing a decimal over a fraction. 0.2 over 36, which then I'd multiply the top and bottom by 10 and get 2 over 360, or 1 over 180. So that is our df, which is approximating the actual change in the function. Now, that's a little unwieldy the way we got there, right? I would like a more kind of set of rules to help me figure this out instead of just being like, okay, well, all this stuff's happening. So here's kind of how we look at this a little more systematically. I'm trying to approximate the change in f. It's going to be equal to approximately the differential df. And the way we're going to calculate that is by saying, well, that's again just our rise. And that's going to be the derivative times the change in x. The derivative is not the challenging part. It's this change of x part that's kind of weird. So I calculated the change of x by actually taking 4% of 5, because that's what they told me, right? They said we're measured at 5 within 4, or accurate to 4%. But that feels like, I don't know, I don't love it. So here's another way you could think about this. You can write this, although this might not feel wonderful either. You can write this as delta x over x times x. You might be wondering why, and I would maybe kind of agree with you. It seems like I've just made it harder than I needed to. But here's what I want you to see with this. This is my slope. And delta x over x is the percentage change in x. Right? You're talking about the change in x divided by x. If I'm 5 and I change by 0.2, 0.2 divided by 5 is 0.04, or 4%. So what this is doing for me is it's allowing me to not actually have to find that 0.2 value that I found in the first place. I know it's not hard to find it, but I feel like it's hard to conceptualize. Maybe it's just me. Maybe I'm like, it's hard for me, and you guys are like, it's totally fine. What are you talking about? But I feel like it's hard to be like, what's this delta x thing here? Whereas this, I'm like, okay, I know delta x over x is just the percentage change in x, or the percentage error, if you prefer that language. And they told us what that was. They told us that was going to be 4%, or 0.04. And then they also told us what x is. This is just what x is measured to be. And I probably need some absolute values, because we're always trying to talk about the absolute value here. It's easy to get lazy with your absolute values if you're not being careful. So then we're going to get our derivative, which we said was negative 136, but I'm not going to do all the calculating again. Our delta x over x, which we know is 0.04, and our x value, which is 5. Oh, look, this is exactly the thing I did in the first place. 5 times 0.04 to get 0.2. So this is the same thing. Oh, sorry, you can see that. That is an approximation of the actual change in f. Right, so if you look back at the original function, which was 1 over 1 plus x, and if you go either 0.2 to the right or 0.2 to the left, it's going to change, go up or down by approximately 1 over 180. Not exactly, but approximately. The other question we ask, or people like to ask when this, where do you think the original function was given to us? Yeah, so it just came out of thin air. Someone was like, here's the function, do this thing with it. Yeah, I know, right? It's like, where, the other thing people ask is, what's the percentage error in f? Well, we already know how to do this if we think about how we talked about this for a second. Right? Delta x over x is the percentage error in x as a decimal. I didn't change it to a percentage. So the percentage error in f is just delta f over f. And then we're going to approximate that with df over f. So we're really just going to take the work that we already did of finding df and divide it by the function evaluated at 5. Because that's the value we're plugging in, which is going to be 1 over 180 divided by 1/6, which looks like 6 over 180, which is 1 over 30. I dropped the absolute values because everything was positive, so I didn't need them anymore. Well, 1 over 30, that's 0.0333 forever. But if they want it as a percentage, we have to multiply it by 100. So it's actually going to be 3 1/3%. Which I don't know how, you probably not want to enter it in decimals, like, or sorry, web work like this, you probably would actually want, I don't really know, actually, to be honest. You might try entering it like that, but I'm not sure. You might try entering it as 10/3%, I guess. Seems kind of weird. All right, let's look at, what time is it? Actually, so do you guys have, I mean, I know this is kind of a lot here. Are there questions specifically about this example that I can address before we do one more? Okay. Let's see. Let's look at that one. So, sure. Oh, wow, that was a lot of cracks. The radius of a sphere is measured to be, let's say, 80 centimeters with a possible error of 0.5 centimeters. We want to use a linear approximation to estimate the maximum error in the calculated surface area. Okay, so we're trying to, and we want to be very careful here. We're not trying to actually calculate the surface area, right? They didn't say approximate the surface area. They said use a linear approximation to estimate the maximum error in the calculated surface area. Okay, it's not too different, but it's different enough that we need to pay attention. I'm still going to do the same sort of thing. I'm still going to use a linearization, right? They say use a linear approximation. So I'm still thinking about this formula. And linearization is f of a plus f prime of a times x minus a. I might use different variables when I'm talking about surface area and radius. Or I might say that my linearization as a function of the radius is f of a plus f prime of a times r minus a, right? Since I'm plugging in r for radius. I don't think it's really that important, but you might think about it that way. So, no clue what the function is here, right? They didn't give us anything functional. They didn't say approximate the square root of 122 or whatever. So what we're going to do here is we're going to say, well, I'm trying to calculate the surface area. So my surface area equation, which I would normally write as like surface area, but I'm going to say it's my function f as a function of the radius r. Surface area of a sphere is 4 pi r squared. That is a formula you probably need to be aware of. So that's what's going to be my function. And then my a value, well, the a value is the nice value they gave us. They gave us a value of 80 centimeters. All right. So if we were going to use the linearization to approximate the surface area, here's what we would get. Our linearization at r would be f of a. Oh, I need to actually plug things in here. So let's see, f of a would be 4 times pi times 80 squared. I should have picked a nicer number. Oh, well, let's just write it as 80. Let's just write it as that. F prime of a, so I need to take the derivative. F prime of r is 8 pi r. In case you're curious, right, this is not a dr/dt situation, right? We're not doing related rates. I have to multiply. I'm differentiating with respect to the variable r, not with respect to the variable time, just to kind of bring it back to that for a second. So I'm going to get 8 pi times, again, I'm plugging in 80 times r minus 80. All right. So if I were to plug in some other radius that was close to 80, I would get my actual surface area. So for example, I would get an approximation. The surface area at, say, I don't know, 80.5 centimeters would be approximately what happens when I plug in 80.5. Why am I talking about this? Well, because here's what's going to happen. Oops. Okay. So we're not being asked to find this. We're being asked to find what the biggest difference between the surface area is and this new, maybe larger surface area. Well, the difference is just right here. This is the difference. This part here is the surface area if the radius is 80 centimeters. And this part here is how much you're adding or subtracting to that to get the estimated surface area of this larger object. So here's another way to think about this, though. This here is really just over here. Sorry, that's almost out of time. So the difference, which we're trying to calculate, is again your derivative times the change, where the a value is the number they gave us, and the delta r is the change in the radius. And we measured the radius accurate to within 0.5 centimeters. So it's literally the same thing as that. So we probably didn't need to do all this. That's okay. It's still good to think about where these things are coming from. If you're being asked just to find the change in something or approximate the difference in something, you're really just doing the derivative times the change in the input. The shorter answer, I know it's 3, if you gotta go, you gotta go. But the shorter answer to this question would just have been say, okay, if I want to find the approximate change in surface area, it's going to be the differential surface area, which is just the derivative times the change in the input. And that's, I know I'm using S and F kind of interchangeably. Sorry, that's not the best notation, but that's just your 4 pi r squared times your delta r. And then if you're plugging in r equals 80, and the biggest possible change in r is 0.5 centimeters, that's what's going to get you this here. That's going to be 4 pi times 80 squared times 0.5, which is exactly the same thing we have right there.
You might take the derivative.
So one more time, Grant.
When you did dsdr, wasn't that 8 pi r?
Oh, thank you. Yeah, apologies. Good, thanks. Yeah, that's a good call. That's the function was 4 pi r squared. The derivative was 8 pi r. Yeah, sorry. I was thinking, sorry, the problem here is the derivative of volume is the surface area equation. So it's easy to get those two interchanged. That should have been 8 pi r. Sorry about that. It should have been 8 pi times 80. Thanks, Grant. Appreciate that. Which would have been 325. All right.